Good morning and welcome to HCII 2022 session on developing VAMR environments. Today, I would like to present our research work entitled Extending Smartphone-Based Hand Gesture Recognition for Augmented Reality Applications with Two-Finger Pinch and Thumb Orientation Gestures. I am Eric Cesar Vidal, and my co-author is Maria Mercedes Rodrigo, head of the Ateneo de Manila University's Laboratory for the Learning Sciences. My talk is divided into four main parts: an introduction to our specific problem, the design of an updated system to address the problem, a usability study conducted on this system, and some concluding remarks. Let's start by introducing the motivation of our system. Our main motivation is to add hand gesture functionality to mobile augmented reality, or AR, which we see as a more cost-effective and ergonomic alternative to AR headsets. We accomplished this in 2020 by creating a framework called Augmented Reality Mobile Device Gestures, or AMDG for short. This framework enables the detection of pointing, air tapping, and opening and closing of the hand to provide AR user interface functionality similar to what is available on, say, Microsoft HoloLens or Oculus Quest 2 headsets without requiring depth sensing hardware. However, at the time, AMDG has several limitations. One big limitation is that AMDG uses a dual camera setup to collect real-world depth data using stereo-based depth estimation. This limits AMDG to smartphones with at least two cameras. Second, AMDG was limited to pointing, air tapping, and whole hand gestures, and more nuanced gestures such as pinching using two fingers were not supported. Furthermore, only the positions of the hand and fingers are tracked. That is, you cannot do gestures that involve the rotational orientation of the hand. Thus, our present study is to design an updated system that addresses these three major limitations. Let us focus first on the first limitation, the need for dual cameras. Our previous solution, as I just mentioned, was limited to phones with two back-facing or world-facing cameras in order to acquire a stereo depth map of the hand. This also introduces additional limitations, such as the AR world being rendered with a very narrow field of view, around 38 degrees only, because the second camera on phones tend to be narrow cameras. The use of two cameras also limits the use of Apple's AR kit, so we are not able to do 6 degree of freedom AR without additional tracking libraries. This inspired us to look for an alternative solution. The main possibility that we considered is to use the person segmentation feature on iOS devices with A12 processors or higher. This allows foreground objects, usually humans, to be detected as a separate depth layer from the rest of the scenery. This has some advantages, including being able to use a wider field of view, and it is also ARKit compatible with full 6 degrees of freedom. But there is one major pitfall: the depth map, or shall we say the pseudo-depth map, that is generated from person segmentation, which tends to be wildly inaccurate and is not representative of actual distance of depth pixels from the camera. This also leads to occasional overestimation of foreground pixels, as depicted in these examples. You will see that person segmentation fails to isolate the background properly in cases where there is only slight color variance, like in this first example, or if the background has certain types of noise, like the grill of the fan in this second example. So, in order to take advantage of person segmentation to eliminate the dual camera limitation, we use an updated skin color filtering algorithm that further processes the pseudo-depth map from person segmentation. Our skin color filter tries to find the predominant skin hue and uses it to eliminate the noise. To do this, first, we acquire the depth map and find the closest depth value. Then we take all depth map pixels within a certain fixed threshold, then erode the result to remove color samples at the borders, since the border pixels can adversely affect our color histogram procedure. Which brings us to the next and most important step. We acquire a color histogram from the original color map of the scene using the eroded depth map as a mask. This histogram gives us the most predominant color of the hand, which we mark in yellow. And you will notice at this point that there are also pink marked pixels, which represent colors that are too far from this predominant skin color, which we can eliminate immediately. As for the rest of the gray pixels, we do a flood fill from the yellow marked pixels. We flood through pixels that are within an acceptable delta of hue or luminosity from the source pixels. At this point, the likely hand pixels are marked in yellow. Finally, we reduce the noise in the output image by doing a dilation and erosion consecutively, which masks any small holes left over for a smooth continuous image. Now, on to the second limitation, how to detect additional gestures. For this work, we focus primarily on the two-finger pinch gesture, which is supported by other modern VAMR systems such as HoloLens, Magic Leap, and Oculus. Our previous AMDG system uses a distance transform technique documented by Lei and Mizukawa to detect the outstretched fingers. This raises a problem particularly with the pinch gesture because in the process of pinching, sometimes the fingers form a loop which causes the two fingers to be detected as one long curve. For these cases, the distance transform method was not enough. However, a previously known solution from the developers of an AR chess system uses what they call a hole-in-blob algorithm, essentially finding an internal contour within an external contour of the hand. If a hole is detected, the system assumes that the hand is in a pinching position. Long story short, we simply adopted this solution on top of our existing distance transform solution to detect the pinch state. However, we would like to note one minor enhancement to that algorithm. Since our own system can detect closed hand poses, we use that to address a limitation of the hole-in-blob system where if there is no detected hole, the pinch gesture is cancelled. In our case, we simply transition between pinching and closed hand states, which prevents the loss of tracking. Finally, we address the third limitation, the lack of hand orientation tracking. Other solutions in this problem sphere include the Handy AR system and the AR in Hand system, which are both limited to 5-finger open hand poses, meaning that you have to outstretch all 5 fingers of your hand to accurately track the hand's rotational orientation. A more recent system, Google's MediaPipe Hands, uses a large dataset of hand postures to track hands in many different orientations. Unfortunately, that means you would have to use much of the processing power of your phone just for processing hand orientation. And even then, the MediaPipe system would have persistent tracking problems, particularly with closed hand poses in multiple orientations. Basically speaking, tracking hand orientation, especially a closed hand, is a hard problem, primarily due to the lack of detectable features of hands when performing this pose. So we got to thinking about this problem and we thought of alternative gestures to the closed hand. And we hit on the concept of thumb orientation. We can just ask users to outstretch their thumbs, and the orientation of such a pose would be tracked easier compared to regular closed hand poses. Practically, a thumb orientation gesture is simply a hand-centered roll rotation. There is only one rotational axis, but that can be sufficient for many orientation tracking cases, including the one I am demoing here, which is holding and orienting a virtual weapon, such as a gun or a sword. There is the possibility of using the phone camera's orientation to actually do the aiming on other rotational axes. Furthermore, this frees up more processing time on the hardware, which can be used for, say, better AR rendering. So, we implemented this gesture to test whether users would be keen on using such a gesture in real applications. Which leads us to the user study that we conducted on our work. To start, let me first show you the prototype application that we used to conduct the user study. The app consists of 3 configurations. First, there is the air tapping and dragging configuration, where the user performs the more standard HoloLens style air tap gesture to pick up virtual objects, and they can just hold the tap to drag the objects around. Here we use a virtual game of Connect 4, where 2 alternating players drop tokens to form 4 in a row, either horizontal, vertical, or diagonal. The second player here is controlled by the CPU. No fancy AI here since the focus of the study is whether users are able to perform the gestures rather than actively beating the CPU. The second configuration is the same game, this time using the two-finger pinching gesture. The purpose of this test is essentially to compare the usability of our implemented pinch gesture in contrast to the standard air tapping gesture as done on HoloLens and also on the previous version of the AMDG system. Finally, there's the thumb orientation configuration. Since Connect 4 does not really have any sort of rotational movement required, we instead created a game where the user needs to turn 3 dials, setting them to a combination that the game will tell the user on screen. The user has to position their hand on top of the dial, grasp it with their thumb outstretched, and turn their hand to turn the dial. Once the dials are set to the correct combination, the game ends. Our usability testing protocol consists of 4 major parts. First, there is the pretest questionnaire, which is a simple Likert scale questionnaire asking participants about their current experience with AR in general, and whether they are familiar with using hand gestures to control computer applications. Second, each participant uses the app under supervision. The goal of the supervised test is to uncover any problems with the usability of the system and whether users are able to perform the gestures correctly. Third, we conduct a usability self-evaluation where the participants evaluate their own performance with the application, whether they found it easy or difficult. To do this evaluation, we use the standard questionnaire called HARUS, short for Handheld Augmented Reality Usability Scale. Finally, we conduct a preference survey, asking the participants whether they prefer any of the three configurations for 7 described scenarios, such as for short-term use, long-term use, etc. Participants can choose multiple configurations or none at all. This will help us determine whether participants truly prefer using hand gestures in a real application, and if so, which gestures do they prefer. The participants were also encouraged to leave short comments on their chosen configurations. We were able to acquire 8 participants for this study. All participants are male, ranging from 23 to 36 years old, in other words, a typical adult male demographic. For the pretest, we asked participants to rate their familiarity with technology topics on a scale of 1 to 7. The results indicate that they have little to no familiarity with augmented reality and AR headsets in particular, but slightly higher familiarity with the applications that use hand gestures and phone-based AR, probably due to the recent explosion of interest in Pokemon Go and similar apps. Consequently, the participants' non-familiarity with AR headsets means that they are likely unfamiliar with the standardized use of AR gestures, such as air tapping. The results of the supervised test are as follows. Only half of the participants are able to complete the air tap and drag test with little to no difficulty. Notably, one participant did not complete the test at all, but it may be attributed to a language barrier because the in-game text was purely written in English, which was not familiar to that participant. Conversely, almost all participants were able to complete the two-finger pinch test. This speaks to the universality of the pinch gesture as a means for picking up small items. Even the non-English speaking participant was able to complete this test. Finally, the thumb orientation gesture achieved slightly less perceived usability than the air tap gesture. This may be because users were currently not accustomed to stretching their thumb out when performing turning gestures on the dials. Also, we discovered slight problems with regards to the continuous detection of the thumb. The Harris usability results paint a very similar picture, with the two-finger pinch configuration outperforming the other configurations, with a higher mean, minimum, and maximum scores all around. Also, the thumb orientation configuration displays a slight usability deficit compared to the standard air tapping gesture, which again mirrors the results of the supervised test. Finally, in the preference survey, it is revealed that the two-finger pinch configuration is overwhelmingly preferred by participants in almost all presented scenarios. To explain this graph, the presented scenarios from left to right are for this particular app, for other AR apps in general, for educational AR apps, for AR visualization, for efficient input, for short-term use, and for long-term use. The only category where the other two gestures are preferred more are for short-term use, where air tapping was the quote-unquote winning gesture. This is actually supported by participants' additional comments, with some testers saying that air tapping can still be effectively used for other tasks, such as selecting items as opposed to dragging them. Also note that for AR visualization, thumb orientation slightly outpaces air tapping as a preferred gesture. Some users noted this preference in the comments, saying that it is an interesting gesture and that it is aesthetically pleasing for interacting with AR elements that require turning, such as dials and doorknobs. To wrap up this talk, we summarize the present study as follows. We were able to significantly improve on our AMDG framework in 3 important aspects: the removal of the dual camera limitation, the support for two-finger pinch gestures, and adding a means for detecting hand orientation via thumb tracking. We also conducted a usability test on the system, which shows that pinching gestures are more preferable to the participants compared to HoloLens-style air tap gestures. And that thumb tracking shows promise as a general hand orientation gesture, with the caveat that it still requires further refinement in order to attain the standardized status of the air tap gesture. As for future work, we are currently gearing up towards the production of full-fledged educational AR and VR apps that will use hand gestures to improve the user experience, and hopefully also improve the learning retention of students using these apps. And with that, we conclude this presentation. Thank you for staying till the end, and we encourage you to check out our other projects at alsat.ateneo.edu.